Okay, folks, get ready, because today we're diving deep, and I mean deep, into the world of blood flow.
Blood flow, huh?
Yeah, blood flow. It might not sound as thrilling as, exploring a hidden temple or something,
Right.
but trust me on this. Blood flow is the engine that keeps us going, keeps us alive. We've got this fascinating medical text, Principles of Blood Flow. One of those things that makes you feel really smart just holding it.
Oh, yeah. I know those.
But we're not just going to show it off. We're going to break it down, find the juicy bits, the mind-blowing stuff that makes you go, whoa, I never thought about it like that before.
A lot of people think blood flow is just this simple process.
Right, like a lazy river just drifting along.
Exactly. But there's so much more to it. There are powerful forces at work, intricate mechanisms that make sure everything runs smoothly.
Right. So let's start with the basics. Blood flow versus perfusion. I remember learning these terms in school, but honestly, I was a little fuzzy on the difference.
Yeah, they're often used interchangeably, but there's a key distinction.
Okay, lay it on me.
Imagine a highway, right? Packed with cars, that's your blood flow. But perfusion, that's about how many of those cars are actually exiting the highway and reaching specific destinations.
Okay, so it's not just about the blood moving, it's about it actually getting where it needs to go.
Exactly. It's about the blood reaching its target and delivering oxygen, nutrients, you name it.
So if there's like a huge traffic jam on the off-ramp, even if there are tons of cars on the highway, that town's not getting its supplies.
You got it. That's poor perfusion, and it can be a big problem.
Yeah, bad news for that town.
Mm-hmm.
So our organs are like those towns, right?
Exactly. They need that constant supply to function properly. If they're not getting enough blood, things start to shut down. That's why doctors pay so much attention to perfusion, especially in critical care.
Makes sense. So how does our body make sure things keep moving, that the traffic keeps flowing? I vaguely remember something about hemodynamics.
Ah, hemodynamics. That's all about the forces that drive blood flow, namely pressure and resistance. It's like physics, but happening inside your body.
Okay, I can kind of wrap my head around that. So, like, the water pressure in my house determines how strong my shower is. More pressure, better flow.
Perfect analogy. Your heart acts as the pump, generating pressure to push blood through your vessels.
And the vessels are like the pipes, right?
Precisely. But just like pipes, those vessels offer resistance to the flow.
Okay, so we've got pressure pushing the blood and resistance pushing back. Makes sense. But what kind of pressure are we talking about here? Is it just high or low?
It's a little more complicated than that. There are actually several types of pressure involved.
Oh boy, here we go.
First, there's blood pressure, the one everyone knows. That's the force of blood against your artery walls. Then you have capillary hydrostatic pressure.
Hydro what now?
It's the pressure inside those tiny capillaries, the ones where all the action happens, the exchange of nutrients and waste.
Oh, right. The capillaries. Okay, so blood pressure, capillary pressure, and what else?
And lastly, venous pressure, which is the pressure in the veins that carry blood back to the heart.
So it's like a whole network of pressures, all working together to keep the blood moving in the right direction.
Absolutely. It's a beautifully orchestrated system.
So,
But you brought up resistance earlier. What exactly creates that pushback against the flow?
well, you mentioned pipes. So I'm guessing the size of the pipes, or in this case, the blood vessels, matters?
You're on the right track. Think about it this way. Trying to push the same amount of water through a narrow garden hose versus a wide fire hose, the narrow hose offers more resistance, right?
Definitely.
Same with your blood vessels. Their length and diameter play a huge role in resistance.
Okay, so longer, narrower vessels mean more resistance. Got it. But our bodies aren't static, right? We're constantly adapting to different situations like exercise or stress.
Absolutely. And this is where things get really interesting. Our bodies can actually adjust blood vessel diameter on the fly. It's called vasodilation and vasoconstriction.
Fancy words. Break it down for me.
Vasodilation widens the vessels, decreasing resistance and increasing flow, while vasoconstriction does the opposite, narrowing the vessels and increasing resistance.
So it's like our bodies have a built-in system of valves controlling the traffic flow in our circulatory system.
Exactly. It's a brilliant way to fine-tune blood flow to different areas depending on the body's needs.
So what triggers those changes in vessel size? Is it like little traffic cops in there directing the flow?
Well, not quite traffic cops, but close. All sorts of things can trigger these responses.
Mm.
Exercise, temperature changes, even your emotional state.
Wow, so my emotions are messing with my blood flow. That's kind of wild.
It's all part of how our bodies maintain homeostasis, keeping everything in balance.
Okay, so besides vessel size, what other factors affect resistance?
Well, there's blood viscosity, meaning how thick the blood is.
Oh, right. Like if you try to pour honey on a cold day, it's super thick and slow.
Exactly. The thicker the blood, the more resistance it encounters. That's why dehydration can be a problem, because it makes your blood thicker, forcing your heart to work harder.
Makes sense. So drinking enough water is like giving our blood flow a little boost.
It can definitely help. And on the flip side, conditions like anemia, where you have fewer red blood cells, can actually make your blood less viscous, leading to its own set of challenges.
So it's like there's a Goldilocks zone for blood viscosity. Not too thick, not too thin.
Exactly. It's all about balance.
We've talked about pressure, resistance, vessel size, even the thickness of blood. Is there anything else we need to consider?
Well, we can't forget about turbulence.
Turbulence, like in the air?
Kind of. It's when the blood flow isn't smooth, kind of like when water hits rocks in a stream and creates all those swirling eddies.
Ah, I see. So rough blood flow.
Exactly. It can happen in heart chambers or large vessels, and things like plaque buildup in arteries can make it worse.
So plaque is like those rocks in the stream, disrupting the flow.
Precisely. And turbulence can make the heart work harder and even damage blood vessels over time.
Wow, so we've got this incredibly intricate system of pressure, resistance, viscosity, and even turbulence happening inside us every second.
It's a marvel of engineering, really. And when you think about how vital blood flow is to every single cell in our bodies,
It makes you appreciate those seemingly small things we can do to keep it running smoothly.
absolutely. Staying hydrated, managing cholesterol, exercising regularly, all these things can have a big impact on this intricate system.
It's like a reminder that even though we can't see it, there's this whole world of activity happening inside us, constantly working to keep us going.
Exactly. And it makes you wonder, how does the body prioritize blood flow when needs change, like during exercise or in extreme situations? How does it decide which organs get more and which get less?
That's a great question. And it makes me realize we've only just scratched the surface of this amazing system.
There's always more to explore, but for now, maybe take a moment to appreciate that silent symphony happening inside you right now, keeping you alive and kicking.
I think I will. Thanks for joining us on this deep dive into the world of blood flow. Until next time.